All right. So, good evening, everybody, wherever you are. Good morning in India and other places, whatever your time zone. Probably good afternoon. Uh, so everybody, good evening, good morning, good afternoon, good evening. So whoever you are, just you're as per your time zone. Okay. Today we are going to have a absolutely very very grueling session, and you're gonna like it. But before you do that, let me show you something. I will share the screen in a bit, but give me a little time. I'm just opening something, and then I'll share the screen, and then we get started. Okay, it's very very exciting. It's very very knowledgeable session. मैं मोदी वाला थोड़ा सा डायलॉग दे दूं.
हाँ दीजिए ना.
Huh? At the end of this session, you will start thinking like an engineer. Yeah, met ki guarantee hai. That's guaranteed. Believe me. That's what. Okay, so I love that Modi when he says Modi ki guarantee hai. I love that. Anyway, so so let's set the screen. I don't know people who there are other American who they didn't understand the Hindi. We are just making some, about Prime Minister of India when he says that this is my guarantee. That's in Hindi. So nothing, we're not saying something bad about you guys. Anyway, so all of you, I guess, can see the screen. So I really wanted to go this, just for 30 seconds. So this is AI Learning Festival, and this is our website. And I'll paste the link on the chat box once again. My problem here, people come here, they register, and that's fine. They registered. That's what they should do, and they're doing it great. But they don't scroll down and see what are the things we are going to cover for next 15 weeks. We already spent 4 weeks. Today is actually from today the real lessons start. But other weeks also as good. Introductory, a lot of exciting things we have recorded. So you'll get access to the recorded version of last 3 weeks, but we are just recruiting more interns, so we are like little overloaded right now. So this kind of a things, we have one intern, he's doing it, and he's a student, he has his own course load. So the things are little taking little time, but bear with us. Eventually you'll get all the recording, but only people who are attending will be get the recording. We're not going to put it on a YouTube or something. It will be on Vimeo with access basis, so you'll be given password and you can access stuff like that. Okay, now having said that, so please come to this, and I will paste this thing, on the. Let me paste it now. Chat. I'll just paste it here so that you can just bookmark this. This is your basically place where also on a. Ravi is there. Ravi, have you joined? I don't know. This guy. Okay. If he has
हाँ जी.
joined, then say it, because he has that. Also, he sent me that we have an instruction on how to join the Discord channel. I'll try to find it where, but I don't have it handy. Then I can upload it, and please join our Discord channel. So this is a week 4. And actually, for the non-technical and technical track, this all the good things are going to happen here. And from the week 4, oh my God, what I okay, from the week 4. So this is my recommendation for the technical people, that you attend technical people track and the non-technical track both, and you will know what I mean when I complete today's session. There's a lot of architectural overview, lots of deep level, some kind of architectural stuff. So I can say that technical, non-technical track is more technical than technical track without the coding. Make sense, everybody? So people who say, "Oh my God, the non-technical track is also technical," no. I'll make it very simple so that everybody understand. But it's like lots of technical things will be there. Every little word, every little technical jargon, I'm going to explain it to you so that you everything will be very crystal clear to you. But it has lots of technical information which will be simplified. So people who are going to attend that technical track also should attend the non-technical track. That's recommended. But if you don't want to do that, if you want to stay with the technical track, it's fine, but it won't give you that, you know, like 50,000 overview of how really everything happens, because that would be very handy for your interview. Okay. Uh, and like today's session is very important. It's for everybody. Think like this thing. And after today, every week, there's a deep level, deep dive, like a master algorithm, mass for technical and non-technical track. If I put for this year on the technical track, then all the people on the non-technical people will be left out. I don't want to do that. So basically, master algorithm is absolutely important. It's a technical subject, basically. Absolutely. What is master algorithm? So I'm going to spend that, and then there is a deep dive into some kind of what you call digital transformation, then AI, and all those things. So please attend that. From today, everything will be very, very interesting. Lots of information. If you want to take, write down notes, please go ahead and do that. And this will be recorded portion of every session will be available to you eventually. I cannot promise when, probably in 2 3 weeks. And then you come back and basically you watch everything, all the recorded words. A non-technical track is very useful for CTOs and CEOs, very, very high level architectural stuff. So you invite them, you can implement within your company. People who are really want to get into consulting business, who are project manager and all, they don't want to get into all the technical things, but still they have the technical knowledge to do some high-end stuff. So this is very important, the non-technical. And we will be also talking about how to really get into consulting business. And if you really master all those things, you can stay with us. You can partner with us. And consulting business is really, really high-end stuff. Very few people will be there. In USA, I don't know, in other countries, the rates really are very, very high. Somewhere between $100 to $400 an hour. That's kind of a consulting rate you can, uh, you know, you can basically get, depends on your skills and other things. But so that is also in a very, very lucrative area, and very few people are there. So we are inviting everybody who just cannot get into the uh, you know technical stuff, is too, because they passed that age or didn't want to get into that anymore. So but they have a vast experience in software and other stuff. Please stay with our non-technical track and come to us. And we are building some kind of ecosystem. So you will be with us, and there will be a lot of consulting offered through us, and we'll be looking for some consulting also. So if there is any opportunity comes to us and we need more consultant, we can really, ask you to join our team or something like that. So it's very important. I just wanted to give you this head start. Okay. Now, that's about it. And I guess everybody, lots of people joined. And so today we are going to talk about our topic is engineering innovation. So I'm going to the topic is called Think Like Wright Brothers. So I'll give you some basically a background of this. What is Wright Brothers and what happened? This gentleman, his at the left, is his name is Professor Langley. He was a professor of mathematics, and he formed a team of, say, I don't know, 7 8 top mathematicians. And at that time, US Department of War gave him $50,000. They used to call Department of War in 1900, more than 125 years ago, almost 125 years ago. And $50,000 in those time. I don't know how much one of our financial friend here might tell us what will be the today's valuation, but at least $10 million. And that was like a down payment the US Department of War gave him, and say, hey, Professor Langley, this is the down payment. You invent the aircraft, and then if you need more, we can give you. And those times there was Andrew Carnegie was one of the top rich man, and he endorsed that project, and he gathered all kinds of top mathematicians and all those things. And he has like a aeronautical society and all kinds of United States Naval Academy and all those things were associated with the top researchers. But that professor failed. But whereas these two Wright brothers, they're my hero. One of them is just a high school, another them is not. They succeeded. Okay, so what, why they did that, and why Professor Langley did not do it, we're going to analyze today in terms of what is engineering innovation, what is engineering reasoning, what is critical thinking. It's a very, very interesting things. I'm going to go through step by step. There will be a lot of diagram I'm going to show, a lot of analysis I'm going to show. Please pay attention, stop all the background noise, and I can tell you that you will be really, you'll like it, you'll like it. Okay, so having said that, so let's start with a movie. I always want to start with a movie. Somebody please start admitting other people. I'm talking now, so please pay attention. Okay, so because I'm also talking, and at the same time I'm admitting people, so please somebody
No
do.
worries, Dada. We are doing that.
Okay, so this is the movie. Let's watch a little movie. Let's see.
1903 recalls the first flight of this primitive biplane making aviation history. As the two brothers prepare to attempt the first catapulted takeoff, man's age-old dream of flight becomes a reality.
Oh wow! See, this created. Oh my God! No, 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 not it. Sorry, some ad really started. This thing. So anyway, so this is what happened. This, you saw the history. Okay, and I see that that particular, I think it's a 40-second video. Probably I watched it like a 1 million times. Every time I get depressed, I watch this. Okay, because that gives me so much energy. That's called engineering. Okay, so we are going to talk about that. Why Professor Langley failed, and what is engineering reasoning. So let's begin with that. So you see this. So the welcome to the world of engineering innovations. Okay, so we are going to talk about this. We are going to talk about all the diagrams. So in the twilight years of 19th century, this thing, some kind of I liked it constantly. Wright brothers and Orville brothers, I already talk about this, why they succeeded, why they fell. And please pay attention to all the lecture. And the last lecture mm, I'll open a PDF document written by a professor of mechanical engineering, and then why. And he just literally, it's some kind of a research paper, but he put it all the Wright brothers design process in that. And at the end of things, when I read this and explain it to you, it will make sense. Okay, before I do that, let me show you something here, and this is very important. You really need to see this. Oh my God, where is it? Okay, so everybody can see this diagram. Okay, this is the diagram I've been posting also on the LinkedIn. Okay, so if you see this, and this is a research, some kind of a research of the skill required by 2028, which is like a 4 years from now, what companies will look for in kind of AI talent, and what kind of skills they are. I have the detailed research paper. I don't know where it is, but I'll upload it on the Discord channel, and it will open your eyes. All the how the skills requirement is changing. AWS spent a fortune to do that research with some kind of a research agency. is here, employee respond. I don't know what is that, but don't worry about that. So let's come to the main point. So you can see this critical thinking and problem solving. Number one, 61% of the people, top CEOs and all they interview, they say no. My priority number one to recruit a technical person is critical thinking and problem, because they are asked, what are the top 10 skills you look for a candidate, and 61%, these are the percentage of the respondent, and there are all top Fortune 500 companies hiring manager, research lab hiring manager, all those kind of universities, all kinds of people who hire top talents, engineering talents and AI. You see this critical thinking problem solving is 61%, and then creative thinking and design, we are going to talk all this today. 52% technical, which is the coding, is the third priority. That means if you know all this thing well, and then I will also tell you why it is so, why it is third priority, and then your technical also very important, but these two should be these two skills should be above your technical skill. Your technical skill should be there. It's not like you have a zero technical skill and you have these two skills. It never happens that way. Okay, so don't even think of, oh my God, that's okay. Let me learn this critical thinking. Still, I don't need to learn Python programming. I'll be a AI programmer. No, don't even think of that. But this is as per their priority list, because when you company hires, they have a top 8 or 10 technical skills and other skills they evaluate, and based on that they kind of give some kind of a weightage. Like in my, if I want to hire somebody, I'll give like a these two like a 50% weightage, let's say 40% weightage, and rest of that 60% weightage. Out of that 60% weightage, probably technical skill, I'll give 30% weightage, because you need technical skill, and others like a whatever the weightage I would give, and based on the whoever scores the maximum based on the weightage on my interview process, that guy will get hired. So this is very important. So you'll be given a lot of weightage on these two skills, but at the same time technical skill is very important. You need to learn some programming. You need to create some models. You need to do all kinds of things which we are teaching you. So don't think that this is less important. Yes, this is important, but in terms of the priority and weightage, these two are very important. That's what we wanted to talk. All right. So I just wanted to show this. This is a very research diagram here. So we'll be talking about this in the future. I'll just upload it on the what you call on the Discord. Okay. So this is done. So let's talk about our. You saw these Wright brothers, and then so I already discussed this. So welcome to the world of engineering innovation. Okay, now before I give you that, and you might want to this thing called why that is important. I'll tell you this, and once I go through it, you'll find that it is very important. Why it is important. Okay, so basically, engineering innovation, why it is more important than what is to be like a few years ago. The reason is two reasons. First of all, everything AI is changing everything. So AI is replacing a lot of jobs. When AI is replacing a lot of jobs, so all lot of skills are getting automated. Even programming is getting automated. There's the end of a lot of programmers are going to lose job. Okay, that's for sure. They already started losing jobs. They upgrade it, get into the new this thing. That's a different thing. But whatever the remaining positions, those are being replaced more into AI related skills. That's number one. And number two is once you have to do that, so you saw that diagram that innovation and technical skills are more important, because you have to be an innovator in those kind of positions, especially technical people. Second thing is uh, people who are in US probably know. People who are not in US do not know. Elon Musk funded a company called Neuralink, and that Neuralink, and you might want to Google search it on YouTube, and they have like a zillions of YouTube videos, Neuralink videos about what they are doing. But in a nutshell, Neuralink is doing is they have created a chip, and that chip is can be embedded uh, on a human brain through non-invasive surgery. When I said this earlier also, that means, you don't have that, you don't need a neurosurgeon to open the skull and, implant the chip. Some kind of a non-invasive surgery will be there, and the chip is implanted with your brain becomes internet, basically. It has a lot of other medical, like a paralytic patient can, basically start walking. Alzheimer patients start remembering stuff. And then also, blind people can see. So a lot of medical good things about medicines also happen with the chip. And but the best thing is your chip becomes internet. When your chips become internet, how you are going to take exam of a candidate? Because the guy will just think of it from the Google. He will download all the exam related questions. Everything is available on the internet. So then how you're going to do that? And it's not even required. So education, I'll also share with you education, like yesterday's news. Lots of California state university, top level state universities, they have a decline in percentage of students, enrolling there. A 157 years old college in New York closed, and most of the colleges will be closed. Only colleges which will really remain and relevant at the top, like MIT, Stanford, Berkeley, where they are doing lots of research. The basic, like a 4-year-old colleges are basically a thing of past. So basically, they're like a dinosaurs. They had a role in the history making, but when the dinosaurs' prehistoric role on the evolution process was over, nature extincted them. So similarly, in the human civilization process, education, all those, what you call the industrial revolution and computer revolution and all those things happen. So it plays a humongous role, all the university system all over the world, but they're like a dinosaurs now. Their role is no longer required. New kind of education system will come when your chip is implanted on your brain. So that's, and there is another very interesting. I'll share all those article by Professor Kak, very famous guy, artificial intelligence. He said that all the colleges will be obsolete. So I mean, I supported. I'll show you. There's a Beta Gamma Sigma, which is the college honor society of top 500 business schools. I submitted about what will be the education of tomorrow. Is more of a colleges will be, there won't be any teaching. It will be more on a research and collaboration. I'll tell you why. Because most of the people learn online anywhere. There are like hundreds of places people can learn, hundreds of courses from Udemy to YouTube to people like us, online, all free. And the best part of it, MIT, in my Massachusetts Institute of Technology, that's the number one engineering school in the world, and it produced 100 Nobel laureates. You know what kind of a university is that? So all their courses from first year to PhD level, from basic civil engineering to aerospace engineering, nuclear engineering, you name it, they uh, recorded actual courses of their classes, and with all the class notes by the professor, class work and everything, and they just uploaded on the, I will share that link also on the Discord, free. And so you can do literally what that MIT student is doing. You can watch the lessons, then there will be some homework. You can do the homework. Those assignments are there. Then also how to correct those assignments. You can see those answer sheet also, and there will be other kind of project, group project, whatever they are doing. So all those papers are there in terms of some kind of a PDF format. You can refer, you can watch, but nobody is going to grade you to give you the degree. Who needs a degree anyway? Okay, if you have the knowledge, anybody can hire you. I had a student who was a DNGS college dropout, and he learned Python, and very bright student. He got a job at Google. Okay, so the education and college, by that time you finish college 4 years with $200,000 student loan, all whatever you learn in last 4 years are all obsolete, because things are happening so fast. You know, Whatever you learned even 3 days ago, it became obsolete. I wrote a book and I released it in sometime September, October. That book itself became obsolete in terms of coding. There are a lot of things that changes. I'm revising book. I'm going to release the revised edition in a few weeks, and then I'll have to keep and watch. And probably that revised edition will be valid for next 3 4 months. Again, I have to bring version one, version two. It is an ongoing process. So that's where reason everything is changing, or the education system is not changing that way, that fast. People are learning faster than your college and universities and all. So next, the future of the university, when I give a proposal, that they will be more like a research and collaboration, because people are learning all the modern technique and the latest, technology anyway faster than colleges are providing. And the professors, like they did a PhD in 20 years ago, who cares? That dude did a PhD in 20 years ago. He is irrelevant. Probably some of them are not. They are into writing peer review papers and all, but most of them, you will know more than your own professor, because that guy is did he didn't upgrade his knowledge. He has to constantly upgrade and become relevant. Very few professors are there. That's what the university that is doing later research, they will be very very relevant university. They will survive, and rest of those others will gone, just like a dinosaurs. Mark my word, this is going to happen. Okay, so that's the reason you saw this Amazon research, that critical thinking and engineering reasoning is so important, because you got to be an innovator. And I don't know, probably I passed that age, but hundreds of thousands of innovators like Wright brothers. Wright brothers didn't have any education. One guy was high school, another guy even not, but they had that innovation brain. They had that innovation idea. They have that engineering reasoning. They have the critical thinking. That is what we are going to talk about. That is what is relevant. So today's session is absolutely important for everybody. If you want to be a good engineer, of course you are, whatever you are learning. Some people are still attending colleges. I'm not saying colleges are bad. Do it, but become an innovator first, and then your colleges probably maybe not that current. So you have to be all the time current with the latest knowledge, and especially for youth class, because you'll have to be current your knowledge all the time. Whatever you're learning at the college, fine, you'll get a degree, and also there are very relevant in terms of building your own foundation, some kind of a theoretical foundation you really need. But at the same time, with that theoretical foundation, you really need to look for the latest stuff, what is happening every day, versus like I would say what is happening every hour would be two, but at least what is happening every half a day. So you look for something in the morning, even up around 3:30, 4 o'clock, go and see whether that thing got changed by replaced by something else. But things are happening that fast. Okay, so basically, this is the I'll talk about the engineering reasoning. So there are 9 dimensions of engineering reasoning. We're going to talk about this 9 different parts of engineering reasoning, and then I'll come back and explain it to you. So all the engineering reasoning, and this is, just remember, record all this thing in mind, because when I'm going to analyze the design of Wright brothers, how they invented the aircraft, all these things will make sense. So record it, record it, record it. Remember, pay attention. If required, put it on a note, that okay. And then we are going to go back 120 years ago and see what those two brothers were really thinking. That kind of original thinking, original human innovation, that will never change. Human creativity will never change. Human innovation will never change. That will remain constant. Probably it will take shape in different form, but that kind of a creativity will always be there. So what Wright brothers were thinking more than 120 years ago, exactly 123 years ago, 1900 or before that they started. So exactly that kind of a thinking is more relevant today. We saw that little diagram from the AWS research. You saw it. They are even asking for the same stuff. So this will never change. Your innovation, your critical thinking abilities. Having said that, So what is the critical thinking or regional? This is more like an engineering reasoning. So engineering reasoning always have a purpose, and with that purpose, that means you are going to, invent the aircraft. Okay, so then what then you are trying to seek a solution. Okay, okay, invent the aircraft doesn't mean anything. I mean, how you do that? What is the solution? That's the second part of the engineering reasoning. Then you make assumption. How you make assumption? I'll go to that. But first of all, I'll give you a little bit example. So Wright Brothers, what they started doing it, because I read lots of their autobiography and all, because I'm a huge fan of Wright Brothers. They're my hero. So what they started doing is, with a binocular, they started observing birds. They started there, and they started talking to ornithologists. Ornithologist means the guy who studies bird, some biological guy. Okay, so they started talking and saying, why those birds are flying? What is that shape of the wing? Why that shape of the wing? Why those wings are flapping? Why? Because that wings are flapping, they're getting some kind of extra thrust, what it is. What is that power they're getting? So that kind of original innovation, they're thinking, this is what they're thinking, influenced by perspective. They're making assumption. That means that the all those wings are like that, but why the wings are shaped like that? Then from that assumption, then is there any kind of aerodynamic significance with that? When the aerodynamic significance, that's an assumption. Now they are going to the theory. They were scientists basically. Don't even think that they were high school. They were consulting all the mathematical knowledge, mechanics of fluid knowledge, and everything, released by Smithsonian Institute, and then Royal Aeronautical Society. I don't know, so many, all those places were there, and they are consulting. They are asking for those papers. They are reading it. They are trying to understand all the aerodynamic principles of it, and they're saying, oh, that makes sense, that makes sense. So that's kind of assumption they're doing. And then they collect the data and evidence. We'll come to that. Then they apply concept and theory. These are all part of the engineering reasoning. Then they make inferences and then understand the consequences. This is the diagram I created yesterday. But if I go through all the blah blah blah, all those engineering reasoning in terms of definition. Let's see what I tried to define it, but it makes sense. So what they said, which is expressing a purpose. Our purpose was clear from the beginning, to invent the first powered aircraft capable of control sustained flight with a pilot abroad. That's the purpose. But here is the problem. First of all, the flight need to take off, sustain, and then they need to have some kind of a control to really balance it, because they don't know, nobody flew before that, whether that's going to make a nosedive or they to fly for something, what kind of a control required, what kind of a balancing required. You see, this is the purpose also. They are trying to figure it out, and then they are trying to make assumption, then seeking to figure out something. That's the engineering reasoning part number two. I tell you, this engineering reasoning will you can go to any college, any best college in the world, but engineering reasoning something, it grows within you. It takes years and years. It's not happen, it doesn't happen that way. Because first of all, Wright brothers, they were brothers, but they were experimenting. They're basically bicycle mechanic. They were they were doing that kind of a thing to make a living. That's what only job they had. They had a bicycle repair shop. But while in the bicycle repairing, they are experimenting with all kinds of a mechanical engineering knowledge, from machine tools to all those things. So they were all had that kind of engineering reasoning in that process they are developing. So engineering reasoning will never, nobody can teach you on day one. But you'll have to ask yourself. That's the question. You'll have to ask yourself. You have to find that solution. What is that? What is that? And that's what I said. My title of this today's presentation: think like a Wright brothers. Now think you are Wright brothers. You have given a task. You don't have money. Another dude, Professor Langley, your competition got $50,000, and with all kinds of government help. And you have said, okay, Professor Langley, that's fine. We are poor little brothers, but we would like to try. We'll try. We'll give it a shot. So we are in a different kind of a scenario, much challenging scenario, but you have a better thinking power. when you have those innovation power, miracle happens. Literally, in this case, it happened, everywhere happened. Think of it, think of it, think of it. How we can imagine, how can solve problem, what will be the your thing. That is what engineering reasoning. I'm giving you all the step-by-step process, but something, it should come inside from you. It has to be your internal stuff. That's why great scientists, something, I don't know, they are born, I don't know. I don't think they are born as a scientist, but they become a scientist because of that inquisitiveness, because of their curiosity, because of their uh, constant, seeking of knowledge to solve a problem. What they're doing, actually, they're trying to solve a problem. So how they can solve a problem? AI is giving you that opportunity. Think of it, Wright Brothers or Edison or Tesla, first, electric motor or first electric bulb. There's a huge problem. Nobody even did that. So they're trying to solve that problem. They're trying some kind of a scientific solution for that. That is what our engineering solution for that. That is what engineering reasoning. It will never come from any college. Trust me, it will come from your experience. But that doesn't mean you have to have a 30 years of experience. It can come for you from your even 6 years of experience or 6 months of experience, depending on how we can really apply to sit that, to solve that problem. That's when you try to apply your internal knowledge, some kind of a hunch feeling, some kind of intuitive learning process, then your engineering reasoning develops. Make sense? Everybody, so far, good or bad, say it. I want to hear it. Say
Good
it.
for me. Good for me. Anybody.
Okay, so now, then we are recording assumption. Okay, we are recording assumption. Then you done with some perspectives or point of view, and based on data, information, evidence, we are going to cover all lot. But I'm saying, then you meticulously collect data, experiment. These are all part of engineering reasoning. Okay, and then I'll come back to the diagram. You all know that, and then you express your through and shaped by some kind of concept and theory. The Wright brothers, I am already said this, you will see lots of documents, a diagram, and the final, when I really discuss the final research paper written by some kind of some mechanical engineering professor and some university, I forgot name, but it's there. I'll tell you what is the name of the university. Then you'll say, oh, it makes sense. So this is what I want to do. So then you lead somewhere has implication of consequences, and it entails making a judgment, because you need to also have some kind of a selection process. You have to judge something. Okay, design number one, design number two, design number three. These are the three design. Which one is really good? Which one is really is going to work? So that kind of a judgment process you really need to have. Make sense? So this is the design process. As I said, purpose extension, seek solution, make assumption influenced by perspective, collect data, apply concept, make inferences, and understand the consequences. That means result. Okay. Now, this is what everything about engineering reasoning. So engineering reasoning has all those 9 parts. Now I'm dividing into some kind of a different aspect of engineering reasoning and innovation. If you understand this, whatever I'm going to show you in next 1 hour 20 minutes or 1 hour or so, or probably I'll go a little bit more if time required. Excuse me, because you always start late every day, but you have to bear with us, because I really want to finish this today. And so you have to stay with me. So that's what. So this is the whole thing of innovation process. This is the whole thing of innovation process. If you understand this, every aspect of this we are going to discuss with a lot of diagrams, with a lot of case studies, and then you will understand, and then you will come back, watch this again and again. All the diagram will be available to you, all the different other different research paper will be available to you. There's a site called Google Scholar. So Google Scholar is where you'll find all the research paper in the world, basically all the top peer review research paper. Even you'll find like people who got Nobel Prize because of some research paper. That also research paper will find. If you type on the Google Scholar deep learning, the first research paper that gave birth to the deep learning by what you call Joshua Bangua, Lee Kohn, and Jeffrey Hinton, the famous three people, they call them three musketeers. Okay, those three musketeers basically got the prize, which is equivalent of Nobel Prize. The first research paper will find it. Go download it. If you don't want to understand, don't worry. But try to understand the process. Try to understand the thought process. You don't have to understand all the maths and all. But think what are the steps they're doing? What are the steps thinking? You, even if you understand 1% of that research paper, still you'll understand some idea of those thought process. That's what I always emphasize. You always download a research paper and try to understand. I download all the research paper. Trust me, 90% of them just go over my head. Trust me, I'm just admitting it. But still, I downloaded, I learned it, I try to learn it, and that makes sense. Then I find something. That's where you gain your expertise. So this, so as I said, the engineering reasoning consists of 9 things. So you have the critical thinking, you have the analytical thinking, you have the empirical evidence and experimentation, you have the problem solving skills, you have the quantitative reasoning, you have the system thinking, you have a creativity and innovation, and then there is other stuff also. You have to have a ethical reasoning. Design thinking is a big way. We are going to have a huge lessons in the future. Will be playbook type of lessons where you can really have a playbook in hand, and you can start with having a design thinking. And suppose you are trying to develop basically what you call a product, an AI product, and you have to wear that hat. You have to have that kind of a design thinking process in place. We are going to discuss today. I cannot discuss everything in an hour, but you will understand that in the future lessons, in the future activities. Design thinking will also give you some playbook. So you have to have a playbook, basically step one, step two, step three. So everything will be, I'm not going to spoon feed you, but I'll give you all the guidance, all the materials to really discover your own. The idea of critical thinking, the idea of engineering reasoning, the idea of being an innovator is to discover something own based on whatever the availability concepts are there. That's what innovation is. That's what you need to, if you are a CEO or CTO of a company, that's what you need to put in your workforce. That kind of a culture you need to build. Okay, let them seek knowledge. That's what even I said. How to build innovation culture within a company. How to build engineering innovation within your company. This kind of things I've been posting on Twitter and all other social media. Exactly what it makes sense now when I'm talking now. So you have to really build those kind of a culture within your organization. Absolutely, are people who can really bring those kind of a culture, or who can be a consultant to bring those kind of a culture. Believe me, there's a huge demand for those kind of people who can bring those kind of culture within a company. Okay, huge demand. If you want to be a part of that, join us. There'll be other way we can cooperate. I'm not going to going to into details, but we are also looking to build those kind of a ecosystem, because we will be doing that now. Okay, so there are lots of those kind of things happening. Lots of those kind of opportunities are coming for us. We need to build that ecosystem fast. That's the reason we are doing this. All those things are free. So that's what design thinking all about now. So let's say we talk about engineering reasoning. We saw the diagram, and so this is what happening. And then we talk about analytical thinking. You saw this diagram, so we'll come back to that. Come back and forth. Don't worry. So just think of it. So this is there. So these are the different this thing. So let's talk about analytical thinking. We already talk about. So now this is let's take the first part. Analytical thinking. So what is analytical thinking? Analytical engineers use analytical thinking to break down complex problems into more manageable parts. Makes sense. So you have the complex problem, you're breaking it to manageable parts. This involves understanding the fundamental principles that govern the problem. So you have a problem, and then you need to understand that complex problem and need to break it into pair. Okay, Wright Brothers example, everything, because I'm giving that example because it makes sense. I've been saying it. So Wright Brothers example, first thing is there were glider there. Before that, there were glider. Even they also designed some glider. They flew it, they tried it. But they need a power flight, some kind of a engine, some kind of a engine will take it and power it and sustain in the air so that they can really have an airplane. Glider is not a airplane. Maximum is some kind of a sports, that you can say that even today. Only one person can ride a glider, not like a 20%, some kind of a cabin or something. So that was really needed. So what the problem was, so they broke down the problem. First, the problem is lift. How the aircraft will really, the aircraft they are going to build is going to lift from the ground and float in the air. So that's a problem. That's the main problem. And then how it will be powered so that it goes forward. That's the second problem. Third problem is how it will be controlled so that it maintains the stability. It doesn't do like that, like a kite or something. Okay, so that stability, all those control should be maintained. So this is a huge complex problem. Now they are breaking it into parts. So now so now say, okay, let's have a manageable first. First figure it out, and I'll show you at the end. Let's have only the glider. Let's make the plane without any power, anything. Let's see how it floats in the air, how it gets the lift. So that's a first problem they're going to solve. Then they will add engine to it, then they will add control to it, and then they will make it a plane fly. So you see that they are breaking down the big chunk of a problem into manageable parts. Okay, that's analytical thinking. Then you understand the every principle. Glider is flying, you need to know aerodynamics principle. And if you have uh, studied, this is like a high school physics, Bernoulli's theorem. Bernoulli's theorem gives you that lift. It will tell you why pressure, and when there's a aerofoil, pressure decreases and the velocity increases. Bernoulli's theorem. So they know that. So they understand the principle. Because of the Bernoulli's theorem, aerofoil needs to be designed that way. When the aerofoil is designed that way, it flies, it gets the lift. So that's the principle they understand, the scientific principle understand. Then they identify variable. Variable means how those wings can be designed. It will be a wings made of metal or wood or some kind of a cloth. So, and what are the variables? And if they change the variable, the entire design changes. Make sense? So if the wings are made of wood, it's lightweight, fine. So it might give you a better testing, but it may not be give you some kind of a stability or something. But if it is a metal, even aluminum, it becomes heavy. If it is cloth, so it might get ripped up or something. So those are the different. As they change the variable, the design changes. So this is all analytic thinking. And then they determine interactions. Make sense? So understanding the fundamental principle, breaking down the complex problem, identifying the variables, I said this, and then every engineering problem involves set of variables. I said that it could cloth or wood or something. So that's kind of design variables. So you have to do. Then applying quantitative methods. Analytical thinking also applies involve quantitative methods. Because in engineering, without mathematics, there is no such thing called engineering. Period. In engineering, you will have to have mathematics involved into that, because you have to have a quantitative method. You'll have to have those calculations. Based on that, if there's a method that allows engineer to quantify the different variables interaction. As I said, when you are making the wings made of wood versus metal versus cloth, so different type of wind flowing over the wind. And then because of you have to calculate what kind of a stability is giving, what kind of a rigidity is giving. So those are mathematical calculation. Okay, and I'll come to that. For that they have to build a wind tunnel to do that. And what is wind tunnel? So I'll come to that. But think of it, whenever you change a variable, there is a whole lot of the whole system changes. When the whole system changes, you have to do a whole lot of calculation, theoretical calculation. So those are all quantified. So you have to use mathematics to quantify. In deep learning, huge amount of mathematics is used. You have to be really, really very good at maths if you want to really become a advanced deep learning, kind of a practitioner. And in our course, probably in the advanced course, we will have some kind of a mathematics lesson also in the future. I cannot promise, but if stay within our ecosystem, those things will happen. And at least we can recommend some books. You can really refer to that. Okay, but that kind of a mathematical background is required. Technical is okay, but even if you really want to be a guru of that, that kind of a matter, because now you're bringing the innovation culture, you're thinking like a Wright brothers. So you have to those kind of a quantitative tool to use in your when you change the variables. So that's then example application. Consider design of energy efficient building. I'll give you this is a very good example application. Engineer to start understanding the principle of thermodynamics and heat transfer, because if you have no you are making a energy efficient building, right? The building, you have to understand how the heat inside the building is there, how the heat escapes in the summertime, how the heat builds up in the winter time, how inside becomes cold, and how we can really maintain some kind of ambient temperature. So you have to use the thermodynamics knowledge, which is basically in engineering. You can really, there's a subject for that. It's basically a study of heat transfer, heat and mass transfer. Basically, that's thermodynamics. There's a huge subject in engineering, and people who have studied that, entropy, enthalpy, all kind of a weird calculation. Not easy, by the way. But anyway, so those calculations, then you have to think about the insulation, heating, cooling system, windows design, and all those. So now you got that, you got those equation of heat and mass transfer. You want to make it a energy efficient, that minimum amount of power to really run the heating and cooling system or air conditioning system. So if that is that, so you have to do all the heat and mass transfer calculation, so that you maintain some kind of optimum level of temperature inside. So those consulators, and then you change the variables, all those heating, insulation, all different kind of parts you are using, moving parts, static parts, all kinds of stuff. So those variables, as you are changing, your calculation changes, your design changes. So that's our quantitative method. So I'll give you an example. This is a very example. I'm very proud of this bridge, because they in India they built it. Is it finished now? I think so, right? So world highest bridge at 359 millimeter on a river bed. And look at this. So basically, so what is the real life example of analytical thinking? Now we are. This is a real life example of analytical thinking. So what is this? They you because this person, this is like they are putting on a river and on a mountain, and the river from here is so deep, and so that and the altitude or the height from this mountain base to the river is, I don't know, several, the 359 above the river bed. So building a basically a pillar from the river bed, and that to river also very very turbulent kind of a water it flows, is very difficult to build a pillar. So engineers thought, "Oh, no, no, let's not have some kind of a pillar. So let's have some kind of a suspended kind of a bridge. In that suspended bridge, so what is the best way to do that? And if you have studied strength of materials, first you'll have to make an assumption. If you make it a cantilever, and with that some wear suspension, what kind of a suspension, what kind of a load it will do, how many traffics will come. Just remember this. So here it is. So understanding the problem, objective, design the bridge, and safety span. It has to be safety, complexity, and challenges like environmental all that time. Winds are flowing. There's very little summer, probably 15 or 20 days. Most of the time it is winter there, and also in on the top of a mountain, very high mountain. And then there's also budget constant. You cannot have like a $3 trillion to build this bridge. So there has to be some kind of budget. You'll have to finish it within the budget. Then you break down into problem like a geographical analysis. What kind of a soil is there? What kind of soil, properties is there? Whether whatever the suspension type of a pillar you're doing with all the rope and everything, and at the end of the two sides, whatever the concrete structure you're building to have those rows and suspension building, all those things, whether that soil can withstand that kind of a load for a long run. What will happen to the vibration when the topic will start coming, because it will vibrate, right? You cannot have like a stable bridge. So those kind of things. So those are all quantitative calculation. Then you analyze the variables, material selection, design parameter, budget constant, and on and on. Okay, now uh, I will. You want to take a break, or you want to? No, let's continue for another 15 minutes, okay? And then we'll take a break. Is that okay, everybody? With it, with that, say yes or no.
Yeah, that should be fine.
Yeah, Sachin said Chennai Railway Beach open in 2022. Good. Okay, very good. I mean, I just wanted to saw that on the Google. I downloaded the picture, then I started analyzing it, how it could be done. This is my own analysis, but just to help you guys to understand what it is. Okay, now I will. I'll come with let's show another movie, very small movie. I love to show you that movie. Okay, I would like you to show the movie. Okay, just see. This is a 2 second movie, not much.
T minus 15 seconds. T minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1. At liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower. Roll program. Roger, roll, Challenger. Roll program confirmed. Challenger now heading down range. Engines beginning throttling down now at 94%. Normal throttles for most of the flight, 104%. We'll throttle down to 65% shortly. Engines at 65%. 3 engines running normally. 3 good fuel cells. 3 good APUs. Velocity 2,257 feet per second. Altitude 4.3 nautical miles. Downrange distance 3 nautical miles. So the 25th Space Shuttle mission is
Now look at what will happen.
After
Watch
more
this now.
delays than NASA cares to count. This morning, it looked as though they were not going to be able to get off.
Oh my God! It exploded.
15 seconds.
It fell.
900 feet per second. Altitude 9
It
nautical
exploded.
miles. Downrange distance 7
And if you
nautical miles.
remember, I don't know how many of you old enough. This happened in 1986. It's called Challenger disaster. It was the greatest failure of NASA, and really this happened. I just wanted to show you. Now we'll use our engineering reasoning to figure it out why it happened and how you can fix it. Make sense? Okay, so this is what happened, and this. I just wanted to show you this movie. I'm analyzing it, and this is happened. These are the crew, and the the worst happened is NASA was so confident. Actually, it is bad luck, basically. I won't say bad luck, but yeah, a little bit of bad luck, little bit of their engineering reasoning failed. There was a school teacher. They put, no, we are not going to have only the astronaut. From now onwards, we will fly ordinary people. So they put a school teacher there and all kinds of people from all walks of life. Only 3 or 4 of them astronaut, and 3, 4 of them, there were 8 crew, were like teacher and something. So the critical thinking and engineering involves evaluating information, argument. On the crisp of morning, January 28, 1986, the Space Shuttle Challenger ascended into the skies from Cape Carnival, Florida. Chris McCullough, a 37-year-old school teacher from the New Hampshire, embarked on a journey to become the first ordinary U.S. citizen civilian explore space, selected from the national competition to join Challenger's 7-member crew. McCullough's dreams were momentarily tethered to Earth by weather and technical delays. However, after 6 days of anticipation, the shuttle pierced the heaven, transforming Macquarie life into symbol of hope, boundless possibilities, and then he saw the disaster. So now, let's put our engineering reasoning and figure it out why it happened and what is the solution. Okay, this is innovation. Okay, so what it happened is, if you know a little bit of aerospace engineering, I won't give you a lot of aerospace engineering lecture here. So when you put a space shuttle, you always put this is a 2-side rocket that's called a solid rocket booster. That's called booster rocket. What it does it when a space vehicle is going to the space, there is something called escape velocity. That means the velocity has to be more than the Earth gravitational pull, because of the Earth gravitational pull always prevent that vehicle to stay within the Earth atmosphere. So you need to have a bigger velocity than Earth gravitational pull. It's a plain physics, 10th grade student knows that, probably he learns that. And then you have to have an escape velocity. Once you have the escape velocity, and then you can really go smooth. To have those kind of export velocity, there are two booster rocket. Basically, the rocket fuel there are two types of fuel. One is like a liquid, where you have all kinds of a liquid, probably, whatever the petroleum product they have, they burn it, and all the jet engine start, and it's called it's ramjet. Yeah, it's ramjet. And then it goes there, and then cryogenic engine and all the stuff. And the solid side rockets, those are all solid rocket. And then a booster, it gives a lot of boost. At one point of time they separates, because when they run out of the fuel, and already the vehicle already took its full thrust to get into that escape velocity, its purpose is done, ran out of the fuel, it separates and fall under some kind of a ocean or something. So when that is happening, what happened, this called this o-ring, you see this are this solid fuel rocket, this thing has different parts, and those parts are basically joined, and in join, and then in between join, there's something called ring. There's some kind of a ring there. It's called o-ring. This o-ring failed. Why the o-ring fell? Because o-ring estimated launch temperature was 29 degrees, and that particular day it was extremely cold. Because it was extremely cold, the o-ring couldn't withstand that cold temperature. So before it was taking off, although there's heat was generating and all, because of the atmospheric paper, a lot of calculation there, this o-ring really ripped apart. When the o-ring ripped apart, these two booster rockets, which are still burning, if we had already burned out, about to get separated from the main rocket, everything would have been fine. But it was still burning, so it just broke into pieces, and this heat explosion really exploded everything. Okay, and the rocket went out of the control. You saw that. Okay, so now this is what is thing. Now keep this in mind. We come back after the break. We analyze with critical thinking and engineering reasoning why it happened and how we can fix it in the next flight. Make sense? Is it interesting? Tell me.
Yeah. Raise your.
Yeah.
You can clap, guys, if you want.
Uh-huh.
Yeah, I'm just saying they can put a clap sign.
So timer, let me put a 7 minutes timer, and then we come back. We might go 10-15 minutes extra. Please excuse me, because we always start a little late, because but a lot of people join. That's fine. So I'll put the timer on, and we come on exactly in 7 minutes. Okay.
Sure.
And I'm back. I hope everybody is back. So,
Yeah.
mm, so let's get started again.
Yes.
Is it? Is it? Can you see the screen? Is it still? Am I still sharing it or?
You are sharing the time clock is coming.
Okay, that means the screen is there, visible.
Yeah.
Okay. So now I'm going to. So now this is. So we talk about just. We talk about the Challenger shuttle, space shuttle. We saw the video how it fell. Now let's use our engineering reasoning, some kind of a critical thinking or creative innovative thinking, whatever you call it, and to analyze what happened and how we can fix it. So this is some kind of a case study, but then we'll go deeper and deeper into it. But this is like just to give you what we covered so far. Okay. So mm, so basically, so you said this critical thinking process. So now we are talking about critical thinking. So as you said in the first diagram, like there's engineering reasoning, there's critical thinking, analytical thinking. We already covered analytical thinking. Now we are going to talk about critical thinking. The critical thinking process, this is a diagram. So what it does, let me come back to diagram after that. So critical thinking process, evaluating information, arguments, identifying assumption, making judgment based on evidence, assessing the reliability of data, considering alternative solution, weighing pros and cons and outcome. So let's see. This is the thinking process. We see this O-ring failure at the low temperature. That they figure it out. I won't go into details how they figure it out. It's more of a extensive aerospace engineering stuff. So let's say they figured that out. O-ring failed. Okay, let's because I cannot go get into all the technical details. Even I also don't know a lot of stuff. Okay, so then because because of that, O-ring fell because of the temperature. Now, how we are going to design it? What are the specifications so that it never happen? So, making judgment based on evidence. And so, is that a hot gas escaping? If there's a hot gas escaping, then what are the design specification that it doesn't fail, even if the temperature becomes extremely, low? And what are the identifying the assumption? The cold war resilience. So you have to have some kind of a wording design that material has a cold weather. Sorry, cold water. What I'm saying, cold weather resilience. Okay. Then you have the re-evaluating the o-ring performance. Then you do the material. What kind of material? You do the material testing. So this is a critical thinking process and accessing the reliability of the data when you are doing testing, how reliable those testing data are, how we can really access those data. Then scrutinizing the material properties, then you really go into the material lab and scrutinize the property in a lab setting. Create some kind of a simulation environment, some kind of extreme cold temperature, then whatever the pressure it really it was withstanding during the flight, that kind of a pressure you created in the lab, that kind of a temperature you created, and say it breaks. And then we have the variables. What are the different variables during that actual flight? You take all those consideration. So this is some kind of accessing all those data. So those you get the real data, because on a place flight, a lot of real data you get. There are many ways you can collect the real data. I'm not getting into that, but you get all those real data. Then you compare with those real data with your experimental data, see what is the delta, find the delta, what is the difference, those kind of stuff. And then considering alternative solution, you redesign the joint. This may happen that that o-ring basically it seals two joint, but when those two joints, if you redesign it, then probably you will change the material of the o-ring, and because of that probably you have to redesign because the material changes. the design specification changes, the O-ring may not fit with the original ring, so probably you'll have to have all the joint, so probably you'll have to redesign it, changes a little bit the specification, those kind of stuff. Okay. Then once these kind of things happen, you weighing pros and cons, then you evaluate effectiveness and feasibility, and then because there's no such thing called 100% perfect design. There's no such thing in engineering. You have to have some kind of a trade-off. That means, if it is safety and other stuff, that's fine, but then there could be some trade-off in design process so that it remains very, very safe and secure, but at the same time, there could be some extra burden. You have to take it somewhere, probably a little bit of extra weight because of change of the material, so that, it fits exactly all the joints, and in that change of the material, probably a little bit of extra weight, or probably if you don't change the material, probably internal that grooving process, probably it will be a little bit different. So there could be some kind of a adjustment there. So, some trade-off you have to always be there in engineering, but you have to figure it out whether really this trade-off can really give us the desired output, which is a safe flight, or it will be again another big disaster. So this is all critical thinking process. This is all engineering thinking process. Trust me, in my last 30 years of engineering career, I have interviewed hundreds of engineers in different position, in different capacity, and from top colleges. Very few people, I ask this kind of question, I don't ask technical question. Very few people had this kind of a critical thinking abilities. That doesn't mean they are dumb. They're smart people, but the education system, the education they receive from the college, doing math, this, that critical thinking process in the education wasn't there. They were not taught that way. And that's what Indian engineers without borders, there's a huge bridge, a gap in there. So we are going to bridge that gap. So bring you that real innovative thinking in that engineering process. So that is what the idea is. Makes sense? So now we are talking about it. I would like to, this is very interesting, this thing, and later on, so I'll go a little past, but I really want to stay here because this is very interesting. And ideally you saw that, now you saw it felt, you saw the design critical thinking process, you saw how the design different assumption, variable, material change, all those diagram. If you understand, we are evaluating, we are doing that, we are doing the calculation, we are weighing our pros and cons, we are considering alternative, we are doing testing, we are getting data. This is all critical thinking process. But if you put it in some kind of a words, it's a evaluating information and arguments. Engineers began meticulously analyzing, same what I'm saying, flight data, material testing result, design specification, what I've been saying. Then identify the assumption. What is the assumption? Original design assumption regarding the O-ring performance. So we take out the drawing. Okay, let's see why it fell. Let's take out the original drawing. Let's see what happened. Why? And when it's a space flight, it's not riding a bicycle or some kind of a car, because you have everything recorded, all the simulation, lab testing, this, that, before the flight, before building the prototype, all kinds of data, all kinds of available there. So bring out that, study that. Okay, we did this, but why it fell? Why the temperature fell? Because of the temperature, and then why it happened? So if you study the original, then what will happen? There's something called root cause analysis. Okay, Japanese invented that, is called why. So any system fell, so you basically ask why it fell. O-ring, why it fell? O-ring fell because it did not sustain the cold temperature. Why it did not sustain the cold temperature? Because the material fell. Why the material fell? So you go down why, deeper. Ultimately, you go to the root cause. Because of this, it fell. But before that, you'll have to ask series of why. In software engineering, probably by that time you reach 5 why, you get the answer. But in this kind of a aerospace, probably you'll have to go down probably you will have a 9 why or 10 why or 12 why, because you are going, okay, because of this happened, because of this happened. So you are going with why. That's called root cause analysis. So with the root cause analysis, you understand, you gather the original data, then you say what are our original assumption, what are the original assumption, and in that assumption what went wrong, what was our thinking process. We are basically understanding time to our thinking process, that in that thinking process we made a little bit trade-off, because engineering design is always a little bit of trade-off, this and that. In that trade-off discipline, what kind of a testing we did, and in that testing what the result there, and what are the assumption there. Did we ever think of it, hey, given all the Florida weather and all, there could be sometimes the extreme cold temperature. Did we really ever test the material in the lab in those kind of extreme cold temperature? No. Why you didn't do that? What was our lack of in that thinking? In the engineering, reasoning, critical thinking, you don't miss out that one. Temperature is a big thing. Why you miss out that? Okay, so those are the real original critical thinking. You're getting down and down. Now you're coming back to that so that you don't repeat the mistake again. Okay, so when you that, then you correct it, and that is why you correct it. So you are all the design stuff and everything, you will correct it, but first you have to correct your way of thinking. You correct it, your way of your analyzing things, your reasoning, this is all engineering reasoning. This is comes through years of experience and years of thinking innovative way. Okay, nobody teaches you in college or something. Okay, there's a very good book by a Naval Academy professor, and I can recommend. It's full of maths and all. You'll get bored. I read that. I get that. A lot of ideas there, but that's more for researcher. So for a practitioner, it would be too hard. Okay. Then considering the alternative solution. Now, what are the alternative solution to this? If the wording fails, what is the safe temperature? What is the safe temperature? Can it go to like a minus temperature? No. Then probably up to 10 degrees temperature it can take, or up to minus 10 take. After that it might fail. Then in that case, where we'll launch it? Whether the Florida, from where they launch it, was the right environment or atmosphere to at that time of the year. If it is not, where other places we can launch it. So those kind of assumptions you have to do, and that is what you will be doing. So this is all critical thinking. Then you weigh pros and cons. If this happens, that happens. If this happens, that happens. Then you have a different alternatives. And after that, you come to a conclusion. The outcome is the critical thinking process led to redesign the solid rocket booster. SRB means solid rocket booster joint, because as I said, it's separate, because it has a fuel in every part. One people burned out, it said, gives a little bit of more weight, more lift. That's a complex stuff, but it gets separate. So that's what the design, the solid joint, including the addition of a o-ring to act as a fail safe. So that's okay. If this happens, probably there could be some kind of another o-ring that can support it. So that's they did it. The introduction of heaters to prevent the o-ring temperature from falling too low, and probably they put some kind of a heating coil or something around that ring, so that when temperature is really too low, the heating coil heats up, and this really heats up this. That's what they did. And then what are these? Then also several modification in enhanced safety. And so there are other modifications. The changes were instrumental in improving space shuttle safety and reliability, allowing a success return flight. And because of that, never those kind of things have happened in the history, because once NASA has this, all the space agency, they got the knowledge, because all the space agency good. One thing good about that, even US and Russia even collaborate in space. You know that? Nobody knows, because they're scientists. There's a hell with Cold War and all. We are scientists. We are engineers. We don't care about borders. That's why we created Indian Engineers Without Borders. So they collaborate at that kind of a research level. They exchange research level. They're not stealing each other's science or anything. They're exchanging those kind of a knowledge. So it's going to all over the world. Moscow, India, ISRO, or whoever the space agencies are there in the China, they are implementing. They understood that kind of concept. This has happened when they have a solid booster rocket. They know this kind of a O-ring might go bad, or this kind of a disaster happened, and that kind of knowledge they already gained from this, and now those kind of a disaster never happened. This is engineering. Okay, man. Okay, so now creativity and innovation in engineering. Now let's go to the next topic. So creativity and innovation in engineering are essential for pursuing. Now we'll go little faster because there's a whole lot of things to cover, and then I'll have to finally do the analysis of Wright Brothers design. Okay, so creativity and innovation in engineering, define creativity. So now all the creativity part comes here. So creativity involves generating original idea and approaches to solve problems and address needs. It's about seeing beyond the conventional solution and imagining new possibilities, innovation and practical application of creative ideas and produce. I'll give you some example. So you have the original creativity, and I'll come with some example, that some kind of a new creativity thinking in engineering. I'll give you a example of smartphone. Steve Jobs. Okay, they basically came with the idea of iPod and everything, and they came with the idea of tablet. Actually, tablet was the first idea before the smartphone. Apple, iPhone. And then Steve Jobs said, "Wait a minute, let's shrink that tablet, okay, a little bit, and make it like a 4-inch screen, and then put the phone and everything in it there. Let's see what happens." So that's kind of a creativity. That's kind of a creativity is talking about. So it's solving an unprecedented problem which was near there. Nobody, because I was working with a startup company with some speech technology. That time somebody wrote an article. I wrote it in some IEEE magazine or something, and they uh, wireless protocol, and somebody said what was not originally possible or something. That was the tagline. Now wireless cannot never happen because it's so complex in those days. So only thing is you can have a phone, cell phone, but you cannot have the internet on the phone because broadband and phone signal are two different things. So all those kind of a problem, they've never heard of it. They came out and with this thing. So Tesla car, I'm giving an example of Tesla car. Nobody even thought of electric vehicle. How can you say that? Because we saw, when we were kid, electric, tram and electric buses and electric train, but always there's a some kind of a wire and it carries it, and there's some kind of a electric wire that goes on top of the vehicle, and it carries just like you go to San Francisco, Simuni, and in India, if you go to places like Calcutta, there's a tram. I think they have that. So those kind of a electric running vehicle or electric train, but nobody thought of electric car because how can you have that? It's not possible. You cannot have those kind of a cable coming out of the electric wire and running your car. It's not possible. Car needs to go everywhere, like everywhere. So the original problem was, hey, how can you solve that? Then why don't you have some kind of a battery that can really run the car? So Elon Musk came with the electric vehicle with some kind of battery. So these are all innovation thinking. It is all creative thinking. And then there is another innovation thinking, renewable energy, technology, biomedical energy, smart cities. This is very important. We have a lot of expertise on smart cities. So this is a hybrid cloud, how we can really. So nobody thought of like 20 years ago, nobody thought of smart cities. Now everybody is talking about smart cities. There's camera everywhere. There's IoT everywhere. There's all kinds of sensor everywhere. Are you still sharing? Yes. You are sharing screen. Can you see the screen, or what is he asking?
I can see the screen.
Okay. So there is a smart city. You see this? These are all the cameras coming, and the camera. There's edge location. There's cloud computing, and there's some kind of near edge location, far edge location. These are all creative design to make the city secure, totally secure. Camera, sensor, this, that, energy efficient. You name it. Okay. We are going to also have different. I don't know when. So these are all in the pipeline. Stay with us. We'll have a different course on smart city. We'll explore a lot of things, what goes into the smart city, how to design a smart city, all those kind of things. Okay. So that's about it. So now, for studying creativity of innovation, you get it what I wanted to say. So if you come here now, this design makes sense, and what it says is this is the design of the creativity basically. Productivity, new improved technology, turning ideas into solution, defining innovation, real world impact, defining creativity, imagining new possibilities, seeing beyond conventional, generating original ideas, practical application. This is all creativity, innovation thinking. Seeing beyond conventional. Cell phone was conventional, but put a internet inside the phone and on a screen, that was seeing beyond the conventional. Car was conventional. To run the car with a battery was not conventional, unconventional. City was conventional, but to make the city smart with all kinds of gadget, IoT, this, that, then it unconventional. So you see what I'm going. So this is all creativity and innovation. So we are going that we did this. Then first studying creativity, innovation, already talk about it. I just want to pass this. And then this is something called, wait, this, I hate this. Why this guy? This always this thing, system thinking. The component of system thinking. Now you got the critical thinking, analytical thinking, creative thinking. Now we are talking about system thinking, how the system thinking works. So let me first go to the definition and come back to this thing, the system thinking. Let me see how much time we have. We have enough time. Okay. So I'm just trying to go a little bit fast on that. Actually, these are all like a 1 day's, workshop, at least 4 hours. I'm trying to quiz it in 1 hour and some minutes. This is very vast subject. Okay, system thinking is a holistic approach. Now it's called holistic approach to analyze that focuses on the way that system constituent parts interrelate and how the system works over time and within the context of large system. So system, if you have studied a subject called control engineering, the control engineering, anything, there's a system and there's a boundary of the system. Okay, and within that system, within the boundary of the system, you'll have to design something and you have to create some kind of a boundary of the system. I'll give you a very example of a good example is uh, a home refrigerator. So home refrigerator has a compressor, and then there's some cooling stuff, and it cools it. So there's some heat and mass transfer. Your internal this thing is air is taking out hot air, and the cold air is circulated to compress air, and goes through some kind of a coolant, or and then the compressed air discharges some temperature because it gets compressed, and the coolant acts as a catalyst to it. Air gets cool, it gets into the gets circulate throughout the refrigerator. For a deep refrigerator, the rate of the circulation is much higher than the lower part of the refrigerator. So there is a system there, and in that system you have the boundary. You have to design everything within that boundary of the system. You cannot design a compressor to cool the entire room. For that, you have a room air conditioner, not that fridge air conditioner. So every system you have a boundary. Within that boundary, you have to understand. So in that boundary kind of a thing, it's very very control system engineering stuff. You know, so you have to understand that way. Okay, so that kind of a system. Uh, uh, I still remember there's something called Nyquist criteria, Howard's calculation, all the stuff. Very complex stuff. I don't want to get into all the thing. So in that system, you have to see that interconnectedness between all the parts, moving or non-moving parts of the system, because we are now creating a system. Within that system, everything works. Feedback loop. Identifying the positive and negative feedback loop within the system. Positive feedback loops amplify the system output. Negative is that this thing. System dynamics, analyzing how system change over time. under the different condition. As I said, that your refrigerator, when it's really hot in the summer, probably your compressor, you know, compressor more air, because it is really demanding kind of a thing, because the ambient atmosphere is so hot that, more hot air, it needs to cool, so it has a different compressor load than the winter. So those kind of a thing. Hierarchical structure, acknowledging the most system are a part of the larger system. So you have the system that becomes a part of larger system and goes on. Let's go through the diagram again, and then we move to that. This is a little complex engineering stuff. I don't know, linger more on this. So at least you understand what is system. This thing, I don't want to get into that. This too engineering stuff. Okay. But at least you understand every engineering design is confined within a system. The system has its own boundary. Within that boundary, there is you design whatever, then, and then in that design, there you think about, how we can really think of in terms of system component of the system. What are the different components? What are the system dynamics? What are the emergent property? What are the hierarchical structure in a system, like a compressor compress the air, then it goes through the some kind of a coolant. So those are high. So this is the step one, this is the step two, this is the hierarchical structure. Then all those other things, insulation, your of the refrigerator, your door, and all is all part of the system. So these are a different hierarchical structure, different parts, that part of the whole system to make it cool. So all those, and as it affects the whole system. What are the interconnected, as I said, compressor. If you have a low power compression, and this thing is refrigerator is very big, you don't give it a cooling effect. If the compressor is okay, everything is okay, but there's a leakage at the insulation of the refrigerator, then there's a insulation is connected with the compressor and the cool air, then there's a leakage, more hot air will come, and then there will be a whole lot, because compressor needs to really make everything cooler and cooler. There will be loaded, and one point of time the compressor will fail, it will burn out. So there's the interconnectedness. Makes sense? So that's kind of stuff. Let's move on. Okay. As I said, system thinking, you can use a lot of things: risk management, sustainability, emergent property, environmental management, urban planning. I'm not going into them, I'm just skipping this slide. And then ethical reasoning in engineering. Ethical reasoning is very important. Absolutely thing. A lot of people are talking about ethical reasoning, computer bias, programming bias. There's a movie in the uh, Netflix called Programming Bias, how that programming really changing, all the algorithm changing. So all the ethical reasoning, how your ethical system, when you're designing a system, how your ethical, because your company needs to be ethical, you're designing some kind of a, lake or something, whether there is an impact in the environment, you're cutting forest to build a lake for the tourists, but at the same time you're destroying forest, or you are building a plant out of nowhere, and there are a lot of, the plant is emitting some kind of harmful chemicals, and then people are surrounding that plant are going to get sick. So those kind of ethical consideration there. I'm skipping this now, so you understood this. So key aspect of ethical reasoning, and then quantitative reasoning. I will stay a little bit on this, okay, and then I'll move on. Quantitative reasoning is, as I said, every engineering there has to be some calculation for any kind of engineering design. I'll give you a small example. If you, a lot of people here in US, not in other countries, they do some carpentry class in the high school. They teach you. So a lot of people I've seen, a lot of my friends, they're very, hobbies. They make tables, all kinds of stuff. At home in their garage to build some kind of, table, or some kind of a structure, some kind of a bookshelf. They love it. There is some kind of a hobby. So even if you do that hobby carpentry, and you are trying to build some kind of table, you have to measure. If you don't measure, you're gonna make a table, even a small stool also. So there is always a measurement. So when you comes to the measurement, okay, there's some calculation involved. I'm talking about building, making a simple, table. Okay, to designing a space shuttle like the one. So as it goes complex, there's more measurement involved, more mathematical calculation involved, because you have to really use some lots of mathematical calculation for any complex design, aircraft design, aerospace, car, you name it. Even nowadays, all kinds of advanced bike, mountain bike. Actually, those are designed by aerospace engineer. Do you know that? Most of the mountain bike are designed by aerospace engineer, not other people. Because that mountain bike is a very, very extreme sport. If people little bit of change in that bike and people will fall, like a 5,000 feet down. So you have to save people's life. All kinds of extreme sports. The bicycle has to be absolutely working in a very, very precise coordination with the pedal movement and everything. These are all done by, this is a huge calculation there. It's all done by cat cam tool and all those things. Figure it out, Google it after this thing. All the mountain bikes are designed by aerospace engineer, because those guys were good at all those kind of precise calculation. So those kind of a quantitative, you have to really create a mathematical model, run those mathematical model. And there is MATLAB is a wonderful example. But they use deep learning for all kinds of engineering calculation, rocket, some space vehicle landing on the moon, those kind of a calculation. Then there is computer aided design. It's called CAD software. Python is there. Then these are all computational tools. Then in understanding quantitative reasoning, what kind of a quantitative reasoning? As I said, you are going to make a little table in your garage. So you have to have some kind of a quantitative reasoning. How long, what will be the height of the table, what is the width of the table, length of the table. So all those are quantitative reasoning. You have to think of it, solving real world problem, mathematical modeling, as I said, linear equation, all kinds of differential equation. You need to build mathematical models. These are all high-end engineering stuff. As I said, that means any kind of a engineering design needs some kind of a measurement, some kind of a calculation. You can do the simple calculation with a little, measurement tape, to very, very sophisticated, mathematical model. Only, like this kind of a, MATLAB and this kind of advanced tool you can use using a very high-end computer. Make sense? All right, let's go. So role in engineering, we got this. Then we are talking about empirical evidence. Empirical evidence is another good area. That is what are using physical prototypes, verifying design, testing before finalizing, empirical evidence, experimentation over theory, testing hypothesis, validation theory. So you are basically, whatever the data, basically empirical evidence is nothing but you have all kinds of data. You have the data from the lab, you have the data from actual performance of the part or the vehicle or whatever, a rocket to bicycle, whatever. So you got the actual data that you recorded from whatever the way you can, and then you have those are all empirical data, and then you see the evidence of your design and what is the delta factor, what is the difference between that. So what kind of an empirical result, what are your testing hypotheses, if you are testing it based on what kind of assumption, what kind of a hypothesis, then how we are going to gather those test evidence for the test, what kind of system behavior it will. So it's all related to testing, empirical evidence, and all kinds of theories. You have a different kind of theories for different kind of design. So these are all gathering empirical evidence. So let's keep that. Pretty much you got the idea. And then design thinking process. I would like to stay a little bit on this. This is very important. We are going to have a playbook for design thinking for all those Fortune 500 companies, or anybody is there. I don't know they are attending my course or not, but if they are very high level, CTO, CDO level, please pay attention to this. We are going to have a separate design thinking process for your entire organization, how to build a data company, what are the design thinking process, how to build turn your company into some kind of a AI factory, those kind of high-end design processing playbook. You have to have a playbook kind of a thing, just like a Super Bowl. Our team, local team, lost, but they have a playbook. Before that Super Bowl happened, they have every movement of the player and the opponent player. There's like a this thick. And every assumption, every movement, the coach sits down for at least a week with assistant coach and the captain or everything. They design those playbook, and based on that, they get trained in the field, and then they go out and play and they win. So that kind of a playbook here, similar type of playbook. Every system will have to figure it out. What are the ingredients? What are the things will come into that? What are the inputs will come into that? How those we'll have to have a separate checklist. Within the checklist, which entire playbook, probably this big it will be, but that, depending on the size of the, architecture, size of the company. So that is all design thinking. Okay, so you define, you articulate the user needs, you emphasize what are the understanding about user experience, user need. User need is very important. I tell you a good example. Nowadays, anybody can really operate basically their bank account from their home. They have to download that, do that. But think of a grandma, 70, 75, 80-year old, and she's not that good at, like a kid, playing with the internet. Even she can do it, because those user system, there's some button, this, that, she clicks that, she gets something pops up. Those all the user, basically what we call usability kind of a design, user-centric design is there in the system, in the app, and then it makes really easy. Ask any elderly person like a 75 years and above, they didn't have remote control for the TV. They would go and change the channel like that. Okay, so but we saw the remote control when the TV came, because it's so easy, because from your home, from sitting on the couch, and that earlier remote control was so complex. Now it's very easy, only 4 buttons. Okay, change the channel, change the volume, and that's about it. So those are all usability thinking. Okay, that kind of thinking. Then iterative process improvement. When you're talking about, you talk step by step process improvement, iterative improvement. I'll talk with that, the final design of the aircraft of Wright Brothers. And also, if you are from Scrum, in the software process development, there is Scrum, iterative process involvement. You have every sprint, at every sprint, you improve something, goes to the somewhere, that kind of stuff. So this is design thinking. And then there are real world application like education, engineering, or I already said this. Then effective communication, this is very, very important, because if your team don't communicate to each other properly, everything goes wrong, even if they are sitting next to your cubicle. Basically, I've seen it. Okay, even in my own company, two guys, they were sitting next to each other doing the same stuff, but still, they're just, when they're talking all kinds of BS. But actual, the design or some kind of thing gets lost. The programming error, it's really, it's glitches. And there is, in the software engineering, we call something, and there is a knowledge difference also. The one guy is very senior, like 6-7 years of experience, another is just a junior, just a 1 year of experience. How they can match each other thinking? So that kind of a communication gap in software engineering, in my company, I introduced, but it's a standard process. A lot of companies follow. It's called pair programming. So you put a senior player, senior this thing programmer, and you put a junior programmer, and let them sit and do the programming together. It's called pair programming. They share the screen. So the senior guy writes first paragraph of the code, and he gives the instruction to the junior guy. Okay, I did it. Now this is the logic. You write the next paragraph of the code. If it goes anything wrong, he tells her, no, you are not doing this. You do it this way. So when they do it, the pair programming for about a week or so, they understand each other. The communication comes better. Then they separate. Okay, so that is the effective communication. One of the way pair programming in my company I did, but it's not like my invention. It was there. Okay, then adaptability, style of adaptation, what kind of a process you are adapting. Every process is different in a Scrum or Kanban and this kind of a thing. Then what kind of a clarity you have. Do you have the clarity in the language, your instruction, everything? Gaining stakeholder support. who are the people, who are the stakeholders in the design process, whether they are going to support it or not. You design everything good. The stakeholder, the CEO, and the marketing guy, and the board of directors, no, that's a lousy product. We don't want that. That's gone. So you lost time and money and everything. So you get to have who are the stakeholders, who really claim that, who will get the ownership of the product. You have to get their support. You have to listen actively. This is very important in design thinking. If you don't listen, everything gets lost. There's noise. And there's a formula. What is the formula? In communication channel equal to n into n minus 1. So that is so if there is a 6 people, so how many communication channel when they talk to each other? So 6 multiplied by 6 minus 1 is 5. 6 minus 5, 30 channel. That's the communication formula. Google it.
Yeah,
if I remember so far. So n into n minus 1. Okay, so that kind of effective communication, everything goes in a 6 people team. Think of it. Everybody's talking to each other at 30 different channels. So those can be very, very difficult. So that's about the communication effectiveness. That's about it. That's done for 2 days. And then we'll go to the Wright Brothers. I just finished it in exactly 2 minutes past 8. Then I'm going to talk about. So far you learn everything. Give me, then I'll give it a little bit filler. Then start into the real design process, critical thinking process of the real aircraft design. Okay, you saw the first clip of that 24 second. Everybody is okay? Was it interesting or is boring? Or was it too technical? Say something, man. So that I know.
Very interesting, and you let everyone basically expand their imagination, and that was the idea here, and I appreciate it. That was good.
Thank you. All right. Okay, now we saw our hero Wright brothers. We saw how we designed. Now let's see their design process. This is a research paper. I'll go by it. I want to spend 10 minutes with it, and then we are done. So we'll be like a 12 minutes over the time. We lost 12 minutes anyway. So this is, I'll talk everything. This is this paper. This is a research paper, and for all the engineering student, research done by Joseph Schillen. He's a professor of mechanical engineering in Saginaw Valley State University. Where it is, I don't know. Probably Australia somewhere, not in the US, I guess. Where he teaches the courses in the thermofluids area and as well as mechanics and labs. Of course, the area of research include experimental investigation of basic turbulence and natural convection. Dr. Schillen received his B engineering degree from McGraw Hill. I think it's in Canada. McGraw Hill University in Canada.
In Michigan, actually. It says it's in Michigan.
Okay, and then PhD degree from John Hopkins. So it's a US, but I never heard of this place. Saginaw Valley, I don't know where.
Yeah, in Michigan. Saginaw Valley State University in Michigan.
Okay. So I highlighted some of the stuff. I really did a lot of study for you guys, So don't, discount me. I really worked hard. Okay. So we are going to spend 10 minutes. You learn critical thinking, you learn design thinking, you learn analytical reasoning, you learn all those, what do you call, all the assumption, or the system thinking. You'll know how to empirical research, you can do it, how the communication do it. All those aspects is now clubbed into original Wright brothers. So think of it, there are 2 brothers, but actually they were actually more than 8-10 people team. So that kind of communication, that. So let's say what he said. The first successful flight of an engine-powered aircraft took place at Kitty Hawk, North Carolina, almost 100 years ago. December 17, 1903. You saw that little video. I don't know. We are lucky somebody filmed that one. The flight was result of pioneering work of the Wright brothers, Orville and Wilbur. Although they barely completed high school, these brothers from Dayton, Ohio have demonstrated that they can truly be considered as design engineer. I want to put a lot of emphasis on that. You don't need to have a degree to become a design engineer. If you have a degree, put it on a this thing frame, put it on a wall table, and your in-laws will be very impressed. Trust me. Other than that, there's no need. At least to me. If you have the design skill, thinking skill, you're part of my team. Okay, that's about. Even I have a degree, by the way. Anyway, I'm not talking about that. But that when you are an innovator, you have to think beyond a degree. Degree has a lot of good things about it. It gives you a theoretical foundation, but also it really chokes your critical thinking process. Why all the scientists in the on the top, Edison, Tesla had a degree, but other what they call Michael Faraday, and then all those big ones, they didn't have a degree. Even Wright Brothers, because they are thinking and not disciplined into some kind of a thinking process, and they just condition into that, and they just believe into that. They're free to think anything, and that's what is required in the engineering innovation. You will have a lot of good engineers, qualified engineers. Of course, you need to hire them. They have the theoretical foundation, but all their thinking process that came out of their rigid engineering curriculum has to be destroyed in the terms of thinking, not their knowledge, the thinking process. They have to be free to think like Wright Brothers. That's what the title of this course is, Think Like a Wright Brothers. Makes sense? So that designing, so what they did is, they can be considered design engineer. They process through rational engineering design process. What are the rational engineering design process? Studying the existing literature of the flight. Of course, you need to do that. Designing and building and testing the kites and tethered glider. That's the second step. The third step is building their own wind tunnel. I talk about wind tunnel. And if you are not familiar with the wind tunnel, what is happen is, there's a tunnel, you can build a tunnel, you put a aircraft model, exactly replica of what your original design, a miniature model, and you put a high-speed fan on the other end, and you put some kind of suspender, and then it goes through that high-speed fan, the air blows, and you see from the study, you can see some glass window or something, whether the aircraft is flapping or stable or something. So some kind of a simulation you do. Nowadays the engineering wind tunnels is very, very sophisticated. It's run by computers and all kinds of stuff. Very, very sophisticated. But those days they didn't have anything. They just built it with some kind of a fan or something, and there's a picture of that. And they built some kind of wooden, pipe, some kind of thing, and put their design there, and change the speed of the fan to have a different flow of the air, and find out in what kind of a, so that's also engineering assumption. You said you are changing your variable. As you change your variable, what is your really final product behaving? You see this is come from this assumption. Okay, so now we got this. So there are 4 stages. The first stage is, example, there is another dude whose name was Maxim. He designed a power flight, but it crashed. It didn't work, and he gave up. He said, nahi hoga. Okay, that's it. So that power aircraft built by Maxim in 1894 was steam powered and weighed 4 tons. Oh my God. Okay, but those days you should give that guy some credit. He did it, at least try. So for scale, notice the man colored willow. This is yellow colored, and that is the aircraft actually a few feet of the ground, and the distance several hundred feet, and then crashed. Okay, it wasn't stable. So that was the starting point of Wright Brothers. Wright Brothers, oh my God, this Maxim, this guy, he already built it, but he failed. You see this on the critical thinking, wording analysis. Now you see how the wording analysis came from this concept. He said, why he failed? Let's study. Let's study what are the assumptions he's made. What are the variable he changed? What are the calculation he did? You see that kind of a thinking process is happened. You see let's look at this. He said Phillips multiplane tested the limit of sequence of 2 wings gave more lift. So they said they call biplane, and you have seen it in the movies also. In the old days, World War II movies, they have a 2 wings because it gives more wings. That's some kind of a design assumption. Those days, very primitive stage of the aircraft development. So he did all kinds of stuff. Okay, so this is even so many wings. He wanted to test it. This guy, Phillips, there's another guy, he did it. That is after this. And then the Wright brothers came, and they were, the Langley was also part of the Smithsonian Institute. They were in competition, but they were exchanging knowledge. Scientists are like that. They're very inclusive people. They're not, oh no, not this. That's office politics. In scientists, in engineering, innovation, there's no office politics. Okay, they collaborate. Even Russia, as I said, Russia, NASA, and Russian Space Agency collaborate at the highest level, not at the political level. So they always collaborate. Okay, scientists are different type of people. You got to think like that. So once having decided to start the project, Wright brothers wrote the Smithsonian on May 30, 1990, requesting publishing papers. Now see this collecting empirical evidence. We are talking about empirical evidence. Is collecting the evidence. From this work, they learned approaches of unsuccessful, some challenges so they got the data, empirical evidence. Now, how did they manage to focus on essential problem to fight so quickly? Both of their brilliance and good working relationship and trying to reason out the problem with two brothers in debating it and debate it thoroughly, and each should reverse his position and debate it. This is communication. We talk about it. So what it is, they would debate, and one guy has a theory, another guy has a theory, they are debating, and they are coming to a conclusion. Then the guy changes his position. So what the theory Wright has, will say, oh no, let's change. So let me debate your theory and you debate my theory. That's the way they communicate. That's why they chant this thing. That's the idea. Okay. Now, and this is the wing, some kind of a kite design. This is the iteration. As I said, iteration. Next step is again to not to build a full scale power club, but build a glider. You see this? You saw this in the diagram that you have to go by step, build a complex. It's the first diagram, the complex problem. Complex problem is a complex because you need to fly, you need to power the flight, you have to all the stability control, you have to have the maneuverability, you have to have a pilot. Those days, whoever guy is, you have to put a man there who can really maneuver. That's flight. Otherwise, it becomes a glider, a kite. So they are doing, so that's a complex process. So they are breaking it into the chunk, that's smaller. The first thing is, let's get it the aerodynamic set. So what is the aerodynamic set? Let's design a glider. That's what they did. Okay, now the second thing is iteration. So they did the glider. The glider, you see this. Now the objective of this still to flight experience. So that's the aerodynamic stuff. And now they built a wind tunnel. Look at this. The poor guy, see this built a wind tunnel like this. And then now Google it, see the modern wind tunnel. This poor guy built a wind tunnel out of wood, and probably, I don't know, other side they had a really electric fan or not. I don't know, probably I have to read that. And they put a model aircraft, and based on that. So look at this, so primitive tools, but still they had the assumption. This is what modeling about. This is all that this thing, because now they're getting all this theoretical thing. Now they're testing, going through that empirical process. Remember, in a wind tunnel, actual simulation, this thing. And then once it is happened, then the third iteration is, then they flew the glider. I'm not going into it. I'll share this with you. Everything is there. You can read it. You already understood. And then they have to have the power flight. They put an engine. They put a stabilizer control. That's the final step. And with that final step, they did it. Now how did these two men essentially alone accomplish so quickly? And which such sophistication, which has eluded great many others for so long. The Wright brothers were inventors of the airplane because they approached the problem with an effective methodology that was undergirded by number of innate talents and personality traits that were especially conducive to technical creativity. You have to have a very, very effective methodology. That's what it is. And this is the process. I'll just go over it, just 2 minutes. Summary of the main design step. Gathering information, we already covered that. Empirical evidence, information, data gathering process, data stuff. Defining analysis problem, analytical reasoning, we already covered that. Then evaluation, then you are doing all this testing and hypothesis, all the design thinking coming into this place. And then you have then you find that analysis, design, and improve the glider, just like a wording. We saw that wording, the glider failed many times. They got the idea, similar like a wording. They get the original design, then they figure it out, what went wrong. They're changing the variables, that kind of stuff. Then evaluation, analysis, and experiment. and then they do the analysis and design, and they correct the design. Just think of a O-ring problem, the same thing they're using it. What NASA did after more than 100 years. And then, not 86 and 1903. Yeah, about 83 years. So analysis and design, they build the engine power, they design and build, develop method and analysis of the propeller. They need to put the propeller because it has to have some power. And then there's a success on December 17, it made history. I also made history that I completed such a grueling and vast subject in 1 hour 40 minutes. This is also a little history. Just kidding. I'm done with that. Any kind of questions, I'll be here for another 4 or 5 minutes to take it. If you want to leave it, you leave it. If you want to take the question, I'm here. And thanks for coming. Thanks for joining. We already start 15 minutes late, and we just completed in 15 minutes. I mean, extra. All right. How was it, everybody? Sachin, how was it?
It's wonderful. It's eye-opening, eye-opener for me. There's so many things.
See,
We
this kind
do-
of innovation we are going to bring to the corporate.
We do all these things, but the all engineering principles in a different kind of the discipline in the is engineering world is fascinating.
Subrata
Right?
Chakraborty, are you the HL person? I don't know. We had a Subrata Da from HL. I don't know is that person. So,
No, sir, I'm not HCL.
okay. No, there because we had a, I had a senior, his name is Subrata Chakraborty, and
It's
he
common name,
retired.
sir. It's common name.
Oh,
Very common.
yeah. So I
Yeah.
thought probably Subrata Da came here, joined, because I'm posting on the Facebook and all, so he's connected, probably he registered, so that's what I asked.
Can everybody put on their camera so that we can have a picture at least, if possible for you, so that we can have a some
Neeraj ji,
kind
how
of
was it?
some kind of the faces we
Neeraj ji,
see
how
every.
was it?
Very good.
Interesting?
Yes, absolutely.
This is the beginning, and you see how deep we'll go for all those digital transformation and all, because this creative and engineering thinking is very, because what happened is, all those large consulting companies, they go and have a playbook and architectural design, but they will never teach you some kind of an innovation to bring in the company, because they teach you all the innovation stuff, they'll lose their business. They said, let them be dumb, we'll come and solve their problem. They'll never teach you how to solve your problem. So you see this, there's so much, gap in that consulting world. And so there's a niche, we can fill that niche. It can be really good in that space.
So Amit, let's have some discussion over here. So can I ask you, Chaturvedi, you are here for almost all the sessions, right? How do you like it?
Sir, it's a new field for me, this AI. So just have been hearing about AI from all the news sources, and when ChatGPT came, a lot of information started coming. So wanted to know what AI is and how I can use it in my professional field, as well as for my personal development also. I'm liking it the way Amit sir is taking it forward. It's quite informative.
No, sir, just call
as
me
well as
Amit, come on. No,
Absolutely.
sir.
From where are you, Chaturvedi? You are in the Bay Area or somewhere? From where you located?
I've joined from Mumbai.
Oh, that's great.
We have another
Yeah.
founder member from Calcutta. Actually, he is Sudeep Roy. I could see him. He is the former chief engineer of West Bengal State Electricity Board. So, Sudeep Roy, please come and say, if you want to say 1 or 2 sentences about the whole thing.
Yes, it's okay.
It's
Fine.
okay?
Keep on going. Yeah,
How do you like it so far?
it's okay. It's engineering related with some MBA also.
Okay. Yeah, he has, okay. Yeah, because that's the need of the hour, right?
Absolutely.
Yeah. Critical thinking and all. Yeah.
Hmm.
Good. Carry on.
Okay. No, so far, because you have attended at least from the beginning, I think you missed one, but all the other session, that's what we are asking. Not for only 2 days.
Yeah,
So
yes, okay, okay.
we have another person.
Okay, we can't hear him. So let's move on to another person. Another person. Who
I
was-
think Ashish ji, you are here, right? He came on the camera for a shot. So where are you from, Ashish? Can you unmute yourself? Yeah.
Hello.
Yeah, give you a brief introduction and tell us how you
Sir, I
like
am
it.
joining from Noida.
Oh, great. And how do you know about this program? Who told you?
Sir, my brother also joined from Mumbai.
Oh,
Recently, you
that's
talked to him, Mr.
oh,
Chaturvedi Singh.
oh yeah.
Okay.
Oh, you are cousin brother. So why? So can you spread up this message to among your other friends so that they can also take the advantage, right?
Sure, sir. Sure.
So please,
Yeah, because we are putting really lots of efforts into it. We are printing
yeah.
out. Okay, so basically, it's rewarding also because a lot of people are getting into it because we are trying to build the ecosystem basically. So we already set up several chapters across the globe, but now we want to spread it. There are a lot of things are happening, so like that.
So I hope you can at least bring 10 of your friends in the next session.
Yeah, sure, sir.
Please, yeah. Okay, it's too late for Canadians, right? The Vijay is already.
I'm good. I don't sleep early, so
Okay,
I'm
so
Yeah,
good.
I have
it's
to,
already 11:30 there.
and
It's
tomorrow
about
Uh,
to.
7 o'clock.
I
There's
don't
a
sleep early.
tomorrow
Yeah,
7 a.m. California time, which is like a Indian time 8:30 in the evening. There's
yeah.
a technical session. So technical session, it will be like a coding session. But even if you don't like coding, but at least I would require you to attend at least first 10-15 minutes just to get an idea what we are doing, and then you can leave.
Okay.
I
You
will
don't
try
need to
to.
do that
So,
coding with me, but
yeah,
at least some idea, how the technical track is getting into the main
sounds good.
stuff.
Yeah,
Okay.
Yeah,
I
Lalit, can
like to
you?
be there.
Yeah.
Thank you, sir. Thanks all of
Okay,
you for
guys.
all the
Thank you
support
so
you
much.
have.
We'll see you tomorrow morning
Okay, see you.
and later in the evening for India folks.
Okay. Thank you.
Have a good night, everyone.